The universe was meant to begin in darkness, its first stars flickering to life in isolation more than 13.8 billion years ago. That's what every expert believed, until the James Webb telescope saw the beginning of time and revealed something impossible. Instead of faint, scattered galaxies, Webb found crowded cosmic cities and ancient giants crammed with mature stars in an era that shouldn't exist. If these findings hold, the very blueprint of cosmic history is wrong, and physics itself may be on the brink. So what kind of universe did Webb actually witness, and how far back can it really see? Galaxies, as we understand them, were never meant to appear all at once. The accepted view held that the universe's grand structures began as scattered seeds, tiny halos of dark matter, each invisible, each a silent architect. These halos, making up about 85% of all cosmic mass, drifted through the early universe, gathering ordinary matter in their gravitational pull. Over time, these small halos would meet, merge, and grow, their boundaries blurring as matter streamed from one to another. The process resembled countless rivulets feeding into larger rivers, each collision and merger building something bigger, a slow, stepwise assembly that favored patience over speed. In this model, no galaxy started out as a giant. The earliest ones were expected to be dim, stunted, and irregular, their stars few and scattered. Each new merger brought a little more gas, a few more stars, a bit more light. The largest galaxies we see today, spirals and ellipticals, are the end result of billions of years of this cosmic construction, with each generation of stars enriching the next with heavier elements. Dark matter, though unseen, dictated the pace and the shape of this growth, providing the scaffolding upon which all visible structure could take form. The mathematics of this paradigm gave astronomers confidence. Computer simulations, run with the best estimates for dark matter's properties, consistently showed the same result. The universe should be a patchwork of small, faint galaxies in its youth, gradually merging and brightening over hundreds of millions of years. Bright, mature galaxies were supposed to be rare, almost impossible in the universe's first half-billion years. The logic seemed airtight. Dark matter halos would only grow large enough to host massive galaxies after enough time had passed for mergers to accumulate. No shortcuts, no sudden leaps. This slow build expectation shaped every prediction about what the first telescopes capable of seeing cosmic dawn, like Webb, would find. Astronomers expected a universe still in the process of assembly, a landscape of scattered, half-formed objects, each one a work in progress. The dark matter halos, though invisible, were the silent organizers, guiding ordinary matter into place, building complexity one merger at a time. The entire story rested on the belief that structure could not outpace its scaffolding, and that the universe, at its beginning, had all the time in the world. Light from the earliest stars never traveled in a straight line. In the universe's first hundreds of millions of years, a thick fog of neutral hydrogen filled the void, absorbing and scattering any starlight that tried to pass through. Astronomers call this era the cosmic dark ages, a time when the universe was opaque, and the only glow was the faint aftershock of the Big Bang itself. When the first stars flickered to life, their light collided with hydrogen atoms, vanishing before it could reach far. The challenge wasn't just distance, but the very nature of the medium between galaxies, a fog so dense that only the most energetic photons could hope to escape. As the universe expanded, something remarkable happened. The fabric of space stretched, pulling the wavelengths of ancient starlight longer and longer, a process known as redshift. Light that began its journey as ultraviolet or visible was gradually shifted into the infrared, its energy sapped by the relentless expansion. For galaxies forming at redshifts greater than 10, their earliest light is now stretched beyond 1.5 microns deep into the infrared, invisible to any telescope designed for optical wavelengths. This shift posed a fundamental problem for astronomers. The Hubble Space Telescope, for all its power, could only see up to about 1.5 microns. That left a blind spot for anything older than about 500 million years after the Big Bang. The first galaxies, the ones that began to rayonize the universe and carve holes in the hydrogen fog, were effectively hidden, too red, too faint, too far. Hubble's deepest images captured only the tip of the iceberg, missing the faint stretched light of the true cosmic dawn. Infrared vision became the only way forward. To see the first stars and galaxies, astronomers needed an observatory that could detect the faintest glimmers at wavelengths up to 28 microns, far beyond the reach of any previous space telescope. This requirement shaped every aspect of Webb's design. Its gold-coated mirrors are optimized to reflect infrared, not visible, and its detectors are chilled to just a few degrees above absolute zero, eliminating thermal noise that would drown out the faint signals from the edge of time. The rationale was simple but relentless. Only by chasing the red-shifted glow of first light through the hydrogen fog, past the limits of older technology, could Webb reveal the universe as it was in its earliest moments. The telescope's capabilities are a direct response to the physics of cosmic expansion. Without infrared sensitivity, the story of the universe's youth would remain out of reach, hidden behind a veil of darkness and distance. Webb's mission is to pierce that veil, turning the invisible into the observable, and bringing the first billion years of cosmic history into focus. The first deep field surveys from Webb arrived with numbers that no simulation had dared to predict. In the earliest data from Cosmos, Webb, and JADES, astronomers counted not dozens but hundreds of bright, compact galaxies in the universe's opening 400 million years. Where models had forecast a slow trickle of faint, scattered galaxies, the actual images revealed a flood. Galaxies stacked edge to edge, their light crowding the infrared sky. The discrepancy was not subtle. In some magnitude bins, the counts ran 10, 50, even up to 150 times higher than the most optimistic theoretical predictions. Hubble's deepest exposures had hinted at a gradual decline in galaxy numbers beyond redshift 9. With Webb, that decline simply failed to appear. Instead, the number of luminous galaxies above redshift 10 remained stubbornly high, and for the brightest objects, the overabundance was most severe. This wasn't a matter of a few outliers. The pattern emerged across independent surveys using different fields and instruments. The JADES team, working in Good South, catalogued more than a dozen galaxies brighter than MUV-20 at redshifts above 11, where standard models allowed for, at best, 1 or 2. Cosmos Webb, sweeping a broader patch of sky, reported similar excesses. Even after accounting for Webb's optical overperformance, an unexpected bonus that let the telescope gather roughly twice as much light as engineers had promised, the overabundance remained, orders of magnitude beyond what any cleaning protocol could explain. Theoretical models had to be stretched to their breaking point, just to accommodate the basic fact. The early universe was crowded with bright, mature galaxies, each one apparently assembled in a cosmic instant. The tension was not just in the numbers, but in the implications. If these galaxies were real, then the universe had built massive structures with astonishing speed, compressing 1 billion years of expected growth into a few hundred million. For theorists, the question became urgent. Were the models missing a critical ingredient, or had nature found a shortcut that no one had imagined? The scale of the contradiction forced astronomers to reconsider everything from the efficiency of star formation to the very properties of dark matter. The abundance of bright galaxies was no longer a minor anomaly. It was the first undeniable crack in the slow build paradigm, a statistical shock that turned a theoretical puzzle into a full-blown crisis. 3 galaxies stand out from the crowd, each one a red beacon against the darkness, each so massive that their very existence seems to deafen the logic of cosmic history. Astronomers call them the red monsters. These are not the faint, tentative smudges that theory predicted for the universe's first billion years. Each red monster contains more than 100 billion times the mass of the Sun in stars, rivaling and in some cases surpassing the stellar mass of the Milky Way. Their light began its journey when the universe was less than 1 billion years old, yet their size and maturity suggest a process of assembly that should have taken several times longer. What makes these galaxies truly astonishing is not just their mass, but the speed at which they built it. By the time Webb caught their light, each had already converted nearly half of its available gas into stars. That's a star formation efficiency of about 50%, 2 to 3 times higher than what is seen in galaxies that formed billions of years later. For comparison, the Milky Way has converted only about 10% of its gas into stars over its entire lifetime. The red monsters managed in a few hundred million years what most galaxies never accomplish at all. Their presence is not just a statistical fluke. In their era, these 3 galaxies alone accounted for nearly 17% of all star formation. They are not isolated outliers, but dominant engines of cosmic growth. The light from these galaxies is spread evenly across their disks, not concentrated in a central core as would be expected if a supermassive black hole were the main power source. This uniformity suggests that their brightness comes from widespread, relentless star formation, not from the glare of an active galactic nucleus. The implications are stark. If galaxies could reach such maturity so quickly, the timeline for cosmic assembly must be shorter and the rules for growth more flexible than anyone had dared imagine. The red monsters force a reckoning with the idea that the universe's largest structures needed eons to mature. Instead, they hint at a cosmos where, under the right conditions, growth could be explosive, where the first giants did not wait patiently for their turn, but arrived fully formed, far ahead of schedule. The question now is not just how many galaxies existed in the early universe, but how any could have become so massive so fast. Jade's GS 14-0 presented astronomers with a chemical riddle buried in the earliest light. Its spectrum, captured by Webb's Ni spec, showed a signature that should not have existed so soon after the Big Bang: oxygen. This element, forged only in the cores of massive stars and spread by supernovae, requires at least 1 full generation of star birth and death. Yet the galaxy's light began its journey just 290 million years after time itself began at redshift 14.32. The presence of oxygen in such a young system upends the expected cosmic timeline. In theory, the first galaxies should have contained only hydrogen and helium, the primordial elements. Heavy elements, known as metals to astronomers, were supposed to trickle into the universe slowly, each supernova enriching the next round of star formation. Instead, Jade's GS Z14-0 spectrum revealed that this cycle had already played out, at least once, possibly twice, before the universe was 3% of its current age. Webb's spectroscopic confirmation left no room for ambiguity. The oxygen line stood out against the faint continuum, a fingerprint of stellar evolution that should have taken hundreds of millions of years to emerge. The galaxy's brightness in the mid-infrared, detected by MIRI, pointed to strong emission from ionized gas, another sign of intense, widespread star formation. The scale of the enrichment implied not just a single burst, but multiple generations of massive stars living fast and dying young, polluting the interstellar medium with oxygen and other heavy elements. For this to happen, the galaxy must have begun forming stars almost immediately after the Big Bang, compressing the expected timeline for chemical evolution into a fraction of what models allowed. The implications ripple outward. If Jade's GS Z14-0 could reach this level of maturity so early, then the entire sequence of cosmic history, first stars, first metals, first complex chemistry, must have unfolded at breakneck speed. The detection of oxygen at redshift 14.32 collapses the neat separation between the era of primordial stars and the rise of metal-enriched galaxies. It suggests that the first star-forming regions were not isolated experiments, but engines of rapid transformation, capable of reshaping their environments in a cosmic instant. The evidence from Jade's GS Z14-0 completes a trio of contradictions. Galaxies too bright, too massive, and now too chemically evolved to fit the slow build narrative. The timeline is no longer a gentle slope, but a cliff. The first era of the universe was not a quiet prelude, but an explosive dawn. At 330 million years after the Big Bang, a new kind of evidence arrived from the edge of cosmic dawn. Jade's GS-1, a compact, intensely star-forming galaxy, was caught in the act of transforming its surroundings. Its light, stretched to the infrared by the universe's expansion, carried a signature that astronomers had never expected to see so soon: a strong Lyman alpha emission line. In theory, this line should have been swallowed by the thick fog of neutral hydrogen that still filled most of the universe at this epoch. Instead, the emission stood out, unmistakable, a clear sign that the galaxy had carved out a local bubble of ionized gas, a transparent pocket in an otherwise opaque cosmos. This bubble, spanning some 650,000 light years, meant that ultraviolet photons from Jade's GS-13-1 were escaping into the intergalactic medium with surprising efficiency. Models suggest that between 10 and 20% of these energetic photons managed to break free, a rate far higher than seen in typical galaxies billions of years later. That level of escape is not just a technical detail, it's the litmus test for cosmic reionization. Where the first stars and galaxies could punch through the hydrogen fog, the universe began to clear patch by patch, revealing the first hints of transparency. The Lyman alpha line in Jade's GS-Z13 was more than a spectral fingerprint. It was a direct measure of environmental change, proof that some galaxies were not just forming stars at a frantic pace, but actively reshaping the very fabric of their surroundings. The evidence from this single object forced theorists to reconsider the timing and mechanics of reionization. Instead of a slow, uniform dawn, the early universe now appeared as a landscape of expanding bubbles, each one a local revolution, driven by galaxies like Jade's GS31. The rules of cosmic history would have to be rewritten, starting with the immediate aftermath of these first environmental breakthroughs. The flood of bright, mature galaxies in Webb's earliest images forced theorists into a scientific standoff. On one side, the standard model, lambda cold dark matter, strained to explain how so many massive galaxies could exist so soon. On the other, alternative ideas pressed in, each offering a different fix for the cosmic timeline. Stacy McGaw, a longtime advocate for modified Newtonian dynamics, pointed out that back in 1998, MOND had predicted rapid early structure formation, decades before Webb's launch. Where the standard model called for slow, hierarchical growth, MOND allowed galaxies to assemble swiftly, bypassing the need for vast halos of invisible matter. But MOND's predictions come at a price. It rewrites gravity itself, and not all astronomers are ready to abandon dark matter's scaffolding. Meanwhile, another camp leaned into the possibility of early dark energy. This tweak to the universe's energy budget could have briefly sped up the clumping of matter, giving galaxies a head start. By adjusting parameters, early dark energy models can smooth over both the galaxy abundance problem and the so-called Hubble tension, the mismatch in measured expansion rates. Yet, these solutions are delicate. A small shift in the cosmic recipe can ripple through the entire model, changing predictions for the cosmic microwave background and the large-scale structure. The debate sharpened as teams ran new simulations, each one tuning star formation rates, feedback, and merger histories to fit the data. Some models squeezed more light from fewer stars, others invoked dense, dust-rich bursts or hidden black holes. No single theory could claim victory. Instead, the field fractured into competing camps, each racing to design observations that could tip the balance. Theorists became detectives, combing through Webb's catalogs for signatures that would support or rule out their favored fix. As the evidence piled up, the only certainty was that the early universe had not played by the old rules. The next round of data would decide which ideas survived the confrontation. The hunt for answers has only deepened the mystery. Across Webb's deep fields, astronomers keep finding the so-called little red dots, tiny, intensely red objects scattered through the early universe, each no bigger than 100 parsecs across. Their numbers defy expectation. More than 300 have been catalogued already, far more than any model predicted for the universe's first billion years. They glow in the infrared, shrouded in dust, their light squeezed into a compact, featureless core. Some show signs of furious starbursts, others hint at black holes growing in secret, hidden behind veils of gas and debris. No one yet knows if these little red dots are the seeds of future quasars, baby supermassive black holes in the making, or if they're simply the most extreme, dust-choked star factories ever seen. Their spectra refuse easy classification. Some carry the signature of active galactic nuclei. Others mimic the reddened light of ancient dying stars. Theorists debate whether they represent a missing phase in galaxy evolution or an entirely new population, one that only Webb sensitivity could uncover. Each candidate is a puzzle, a potential clue to how the first black holes formed and why the early universe produced so many compact, energetic objects in such a short time. Every new survey adds to the list. The deeper Webb looks, the more little red dots appear, scattered like embers across the sky. Their abundance suggests that the processes shaping the first galaxies and the first black holes were far more chaotic and prolific than anyone imagined. For now, they remain enigmatic, each one a silent witness to an era when the rules of cosmic growth were still being written. The quest to understand them is just beginning. Webb's mission continues, its gold mirrors tuned to the faintest glimmers, searching for the next anomaly, the next contradiction, the next question that will push the story of cosmic dawn even further from closure. In its first year, the James Webb Space Telescope confirmed galaxies at redshift 14.32, just 290 million years after the Big Bang, far earlier and more abundant than the Lambda CDM model predicted. Deep field surveys revealed up to 150 times more early galaxies than expected, and spectrographs detected oxygen in the universe's first 300 million years, demanding several earlier generations of stars. Yet the origin of colossal red monster galaxies and the true nature of the little red dots remain unresolved. Peer-reviewed studies published in 2023 and 2024 continue to challenge established timelines, showing that much of Cosmic Dawn's story is still unwritten. As of today, the Webb telescope's ongoing mission is reshaping scientific consensus with every new image and spectrum. The evidence is clear. The universe's beginnings are more complex and surprising than theory allowed. The search for answers continues, driven by data that no longer fit the old cosmic blueprint.